Alright, what's up guys? In this video, we're going to pick up with some multivariable calculus. We're going to be talking about double integrals over rectangular regions. So I'm going to evaluate this double integral, the square root of x over y dA in this rectangular region, or over this rectangular region R. So basically, we talked about before in previous videos, when we're integrating over a rectangular region, doing double integration, we can use Fubini's theorem, which basically says that the order of integration doesn't matter. We can evaluate the double integral dy dx, or we can evaluate the double integral dx dy and get the same answer. Now, a lot of times students don't believe that, so what I'm going to do in this video is I'm going to show you how to evaluate this double integral in both orders and prove to you that the order of integration doesn't matter. We can get the same answer. However, I do want to caution you that Fubini's theorem can only be applied to rectangular regions. It cannot be applied to double integrals over non-rectangular regions or general regions. This theorem does not hold. The order of integration does matter in those regions. This can only work for rectangular regions. It's the same thing for triple integrals over rectangular boxes. The order doesn't matter. So I'm going to prove to you that both orders work. So we're just going to start with dy dx for the first order. So first of all, this looks very intimidating. So we got the square root of x over y dA. So that looks very intimidating, but that's okay. We're going to change that and make that look perhaps a little easier. So let's do this dy dx first. So if we're going to do this dy dx first, well, then it'll be from 0 to 1, and then from 1 to 4. And then recall that the square root of x over y, that's the same thing as the square root of x all over the square root of y, and we're doing this dy dx. So just modify it. So now it doesn't look so difficult. All right, so since we're integrating with respect to y first, we're treating x as a constant, which means I can pull out that square root of x. So let's pull that out, and we work our way from the innermost integral to the outermost one. So the square root of x can come out front. And then this is going to be from 1 to 4. And what I'm going to have is 1 over the square root of y integrated with respect to y. And then we'll integrate respect to x after that. So remember that the antiderivative of 1 over the square root of y, that's just going to give me 2 times the square root of y. And I need to evaluate this from 1 to 4. Remember that the square root of y can be written as y raised to the 1/2 if you want to move it up front, and or move it up top, change it to a negative 1/2, apply the power rule. Hopefully you guys know how to do that by the time you get to multivariable calculus, so I'm not really going to go through that whole thing, but that's the antiderivative of 1 over the square root of y. Now let's go ahead and plug in the upper limit first. So if we plug in the upper limit, we get the square root of 4, which you know is 2, and then we plug in the 1 after that as well. So essentially what we're going to end up having is we're going to have 2 times 2, which is obviously 4. So 4. And then the square root of 1 is obviously just 1. And then we'll multiply that by 2. So we'll subtract. So that'd be 4 minus 2, which is 2. Then I'll multiply that by the square root of x. And so now what I have is the integral from 0 to 1. And this is going to be 2 times the square root of x dx now. So the 2 is just a constant. Remember that the antiderivative of the square root of x, that's 2 over 3, x raised to the 3 over 2. And then this is going to be evaluated from 0 to 1. So we're obviously going to get 2 over 3 minus 0, which is 2 over 3. I then multiply that by the constant that was pulled out front. So that's 2 times 2 over 3, which is obviously 4 over 3, which is the answer to the double integral for the first order. So for the final answer for the first order, dy dx, whereas to integrate, and it was dy dx, just keep that in mind, that was the first order, and we got 4 over 3. Okay, so that's the first order. So now the question is, are we going to get 4 over 3 when we integrate it in the second order? And the answer to that is yes. And let's prove it. All right, so the next order we're going to do is dx dy. And all I'm doing here is proving to you that this works in both orders. So, again, we just have our double integral. Again, use a little algebra sometimes to rewrite things. Sometimes these integrals can be given to you and they can look a certain way. They just look absolutely terrible, but you can rewrite them. So we're going to do this dx dy. So since we're doing that dx dy now, well, this is going to be from 1 to 4. The integral on the inside here will be from 0 to 1, and we're going to modify this again. So it's going to be the square root of x over the square root of y, and then this time it's dx dy. All right, let's try this order now. So we're going to work our way from the innermost integral to the outermost one. We're integrating respect to x first this time. So since we're integrating respect to x first, that means we're treating y as a constant. So I'm going to factor out a 1 over the square root of y. And then this would be from 0 to 1. And I'm just left with the square root of x dx on the inside. So what I get is 1 over the square root of y. We know what the antiderivative of the square root of x is. That's 2 over 3. X raised to the 3 over 2. This is going to be from 0 to 1. So we know this gives us 2 over 3 minus 0, which is 2 over 3. Then we multiply that by 1 over the square root of y. And if we do that, we'll have 1 over the square root of y times 2 over 3, which effectively just gives us 2 over 3 multiplied by the square root of y. Now we need to evaluate it with respect to y. So 2 over 3 is a constant and can be factored out front. And this will be from 1 to 4. And then what we'll have on the inside here, once we factor it out, is just 1 over the square root of y and then dy. So the 2 over 3, remember the antiderivative of 1 over the square root of y dy. That's going to be 2 times the square root of y, or 2y raised to the 1/2, because the square root of y can be written as y raised to the 1/2. And this time, it's going to be from 1 to 4. So we already know what happens. We're essentially going to get 4, because the square root of 4 is 2. So we got 2 times 2, which is 4. The square root of 1 is a 1, so we'll have 2 times 1, which is just 2. So this would be 4 minus 2, which is 2. Then I'll take my 2 over 3. I'll multiply it by 2. And looky here, we get 4 over 3, which is the answer. And that's the exact same answer that we got for the first one. So that's the answer for the second order. And notice how the answer is 4 over 3. So as you can see, when we're integrating double integration over a rectangular region R, we can integrate it in any order, dx dy, dy dx, and get the same answer. So that is the proof that it works both ways. So I just want to do a quick video on that. I've posted videos about it before, but never really did a video. Well, I've posted notes about it before, but never really did a video proving to you that this actually works. And that is your answer. And I'll post a video showing you that this can be done with triple integrals over rectangular boxes in another video. That one will be a little bit more difficult to do, because triple integrals, you got 6 possible orders of integration. So I won't be able to do all 6 possible orders in one video, obviously. But I'll post a video where we evaluate a triple integral over a rectangular box and see if we can kind of modify the order a little bit in those cases as well, just to kind of prove to you that regardless of what order we do it in, we'll get the same answer. But again, very important to remember. I know I sound like a broken record. Very, very important to remember. This theorem only works over rectangular regions. Don't try to apply this theorem over non-rectangular regions. The order matters in those regions. Very important to remember that. All right, guys, hopefully these videos are helpful to you. Let me know if you have any questions, and I'll see y'all next time, and y'all take care.